Dr. Holly Shulman. She's a professor at Alfred University, a research professor. And she also has her own company, Dr. Holly Shulman LLC. And she's a specialist in microwave sintering, specifically for ISRU, for lunar and Martian regolith. So I'll let her present now. All right, there you go.
Okay, thank you. Thanks for the opportunity to present to Florida Space Institute. So I'd like to give you a little bit more background information about me because it seems like I've just jumped into the space scene recently, which is kind of true, but actually I had a previous company called Seralink, and in 2011, NASA approached me for the use of microwaves for lunar and Martian sintering, microwave sintering. So I've been a professor, and now I'm switching lanes to become a research professor. So I'm not teaching, but really my main focus is on developing my new company. So I've been called Dr. Holly Shulman LLC, which was really set up to be a consulting company, but this NASA work has taken off, and I'm changing the name to Blue Star Advanced Manufacturing, and pushing forward really to have that as my main focus, while also doing some work at Alfred University. I get good access to students and the labs there. So Seralink, my previous company, really was focused on working with industry to help them develop energy efficient processes for ceramic and glass. And a big bottleneck there is the firing process. It takes a lot of time and it's highly energy intensive. So using microwaves as a way to speed up that process and also be more energy efficient was really important. And I got a lot of experience involving microwave sintering and vitrification. And I did this for companies and industry, and also leveraged government funding in order to help my industrial clients. And that's when NASA found me on their radar and asked us to work on using microwave sintering for construction. So 10 years later, I've circled back, and I've been working with NASA for about 4 years now, independently of Alfred, but at the university, I've definitely had wonderful students working on projects there as well. So that's a little background information. And so this topic is microwave sintering for lunar-based construction. I gave most of this talk, or a good portion, earlier in 2023 at Material Science and Technology conference. So this is with NASA, and it was authorized by NASA. I've been part of their team, so just want you to know that's my orientation, really. So even though I have a private company, I'm contracted to NASA. So this on the right gives an overview of technology, NASA's technology drive. And you can see I've circled in situ resource utilization, as well as excavation, autonomous excavation and construction. And those are the areas really where I'll be focused. On the left, you see the NASA's moon mineralogy mapper. And you can see that there's a high concentration of water ice that's been located at the North and South poles. So that's very exciting. And so the South Pole is now becoming the destination for the first time for development. The Artemis 3 mission is positioned to be able to do a demonstration landing pad, a small demo on the moon. It'll be the first human mission to land since 1972, and actually the first time on the South Pole. And so that demonstration will be small, but it will be really significant to bring back information and for us to know that we can actually proceed with whichever technology is down selected. And obviously, I'm aiming for microwaves to be down selected. Longer term development of site infrastructure will include mining, refining, building, manufacturing for sustainable human habitation. And this really is set up as I'm sure all of you know, as a launching pad for outer space exploration and Mars as a first destination. So the Lunar Surface Innovative Initiative is the larger parent organization at NASA, and MPACT, or the Moon to Mars Planetary Autonomous Construction Technology team, is out of Marshall Space Flight Center. And their mission is to deliver, demonstrate on-demand capabilities, landing pads, habitats, shelters, roadways, etc. So that's where I fit in under a subgroup of that is the microwave structure construction capability team. So NASA recruited me to lead the microwave sintering part of that team. And this was about 4 years ago. On the right, you're seeing ICON is being contracted to develop the robotics for this landing pad. So you can see a robotic arm, and then the end of that is where we would have our microwave. So that can be interchanged between different types of energy applications. So I'm a ceramic engineer and scientist, and from that viewpoint, I need to know what materials I'm working with in order to make things, right? So it was super important for me to understand more about lunar materials, what they look like, how they behave. And it is just so interesting, really exciting to me to see these things. Regolith is comprised of minerals, glass, breccia, and agglutinates. And on Earth, we don't really have the agglutinates the way that they occur on the moon. So that's a holdup in trying to get a really high fidelity simulant. And it's very important that we develop all of the right ingredients to work with in a very high fidelity simulant so that when we do our processing on Earth in appropriate conditions, we won't have as many surprises as when we get to the moon. When you look at the moon, you can see the darker regions, that's the mare or mare regions, and it's dark because it is predominantly a basalt type material. The highlands area is very different. You see how light it is, and that's because it's got a calcium plagioclase. I'm showing on the right the analysis of Apollo missions, and Apollo 16 did manage to bring back some highland samples. So that's what we base our highland simulants after. And you can see there's plagioclase, pyroxene, olivine in all of these, but the plagioclase is much higher in the highlands region. But these other materials like pyroxene, we can find that on Earth, but it's also really easy to fabricate that. And olivine is even easier. We have large quantities of that. But the plagioclase with a high calcium content is really difficult to find on Earth. And that becomes a problem for developing simulants. And then you can also see the variability for the glass content, with highlands glass really being a combination of all of the things in the highlands regions, the minerals kind of melted and in an amorphous state. These things, I hope I can use the pointer without messing this up. Can you see this pointer at all?
Yeah.
Great. So this is a grain or a rock, small rock of plagioclase, and you can see how white it is. And then you can also see the texture is very different than what we would find on all of these than we find on Earth. And that's a major difference. We have weathering on Earth that doesn't occur on the moon. They have micrometeor impacts all the time that are causing fractures and very jagged surfaces here. Also, their volcanic glass, because of that low gravity situation, forms these very spherical beads. And here's some more. I just think these are beautiful. The regolith is so interesting to me. So here's the very white anorthite, and really it's anorthosite, which is the mineral. A northite is the full calcium version. A northocite has a little bit of sodium, or it can have a mixture. And then the basalt material here, much darker, and the agglutinates, which are a combination of glass and minerals, a very fine scale, and it's very unusual. And there's a lot of questions on how this will affect all types of processing and all types of mechanical properties. But I'm especially interested in the microwave heating aspects, because from the dielectric perspective, they should be very different. And then I just want to share my enjoyment of these beautiful structures. Okay, so there's a real need for high fidelity Highlands lunar simulants, including a dielectric fidelity. So the natural minerals, there's a shortage of that calcium plagioclase, which is a real issue. Just recently, we've gotten a new simulant, NUW LHT5M. And that one has a synthetic glass, and all of the other components are mined materials. So one of the things I did for my NASA project was to look into developing a fully synthetic simulant so that I could really control all of the different inputs, and then also be able to get a range. Instead of just trying to have one simulant, I would be able to make a lot of modifications with control, so that then I could see how that impacts the microwave sintering aspect. And this is really important for process development. This process has to be robust. We can't make some error because when we go to the moon, the composition changes slightly or even drastically. We still have to be able to handle that in real time. I want to point out that the NULHT5M here, these are modeled on the Apollo 16 sample. And the W stands for Washington Mills. So this is a NASA simulant that uses Washington Mills glass that's synthetic. And it's a lot of glass. This was according to Doug Rickman. He has developed this simulant, and there's 40% glass in here. And HQ for high quality, which is not a thing that ceramic and glass scientists use, but apparently for NASA, this means that it's highly amorphous, so it's non-crystalline. So glass is not really purely amorphous. It actually has short range order, but there's, by X-ray diffraction, it appears totally amorphous. And Doug Rickman used norite in that mix, but by using these pyroxenes, we're able to get the exact same chemistry here. So, and pyroxene is actually close, it's what we're dealing with in Highlands regolith. So another aspect is how this material packs down. So our green density, so that's just without any heat of process. The green density is important because it's going to affect the sintering, whether it's microwave or not. And it will, the green density is going to have an effect on the final density, the mechanical properties. So we really need to understand how this, how this stuff behaves. What we're doing for top-down sintering, we're not going to make bricks and tiles in that paving work, but bricks and tiles will be important for construction. I believe we're not, NASA's not focused on that right now. And so what's interesting is we use something called tap density, where you put this in a cylinder, its mass and its volume, and one tap is really what we would call the bulk density. And the bulk density of this material is pretty high, but it's because it has a very large particle size distribution, the more coarse particles kind of like touch up against each other. And then as you tap it, just mechanically, the finer fractions will fit in to the interstices, And so then you develop a higher and higher density with more taps, even to the point where if you pressed it uniaxially, with, reasonable pressure, that you're able to just tap it to that density. And on the right, I'm showing the iconic footprint that shows that you really, would be, of course, with very little pressure. You're really able to form these in a green state very easily. Normally, for most ceramics, you need to add some type of organic binder, which you then burn off later. But because of the ISRU restrictions, I didn't want to use any binder. And I was able to press, these are like 2-inch diameter pellets, able to press, pretty good sized pellets without any problem at all. And we did this on many different types to just to get to understand how we're going to form these things. So there's different ideas for construction on the moon. Marshall is also working on a sulfur concrete with Mike Fisk, who's actually in charge of my project as well. And they're making really good progress. It'll be super important for Mars, where there's a lot of sulfur. But in order to get sulfur on the moon, there would have to be a lot of infrastructure in place already. So it's at a pretty low TRL, technology readiness level, but I think it's going to be very important in the future. ICON has been working on laser sintering, and I'm focused on microwave sintering. So this was early work that I did with my previous company, Ceralink. This is what I started working with NASA, and this was JSC-1A, and we were not in vacuum. We used an inert atmosphere cover gas. And we did a lot of work on both modeling and experiment and being able to understand what was needed for this process, which has translated really well into my Highlands work that's more recent. And if you see on that bottom left, there's a pretty good sized block, something like almost 2.5 kilograms. And I use a figure of merit in kilowatt hours per kilogram to help get an understanding of what's the energy usage, because I'm always focused on energy efficiency. And so in an atmosphere, argon, it's going to take more energy than in a vacuum, because we're also heating that atmosphere. So this was really significant and very useful. And then it's just been fantastic to circle back. That bar there shows a lot of porosity, but even with that, it's giving a strength that is something like a strong concrete or a natural stone paving that you'd find on Earth. So it's a reasonable construction material, even without optimizing anything. But I am learning to understand a lot about that bubble formation. And this is just in argon, but in vacuum, it is more significant and needs process development. Well, I've been working on process development for that. So now for recent times, my microwave systems are not able to pull a hard vacuum. So I went to Marshall and worked over there. And when this project started up about 4 years ago, we didn't have a lot of, any of the NASA simulants in large scale, the Highlands. So they quickly put together a simulant at Colorado School of Mines, and it's okay, but it's got certain issues, and off-gassing was one of those of non-lunar material. So the first thing I did was develop a bake-out for that I also used for JSC-1A to get rid of non-lunar materials. And if you ever see the symbol MB1, I call it bake-out number 1, it's a well-defined process that we do for some low temperature bake-out. So that was the material we used. On the right top, you're seeing a waveguide at the very top, feeding into what we call a multi-mode applicator. So this is to apply microwaves from the top down onto the surface. This is a stainless steel. It looks kind of square like a box, but actually it was modeled and designed to help bounce microwaves around so that you have a more uniform electric field. And that was done by Hal Kemery at Microwave Materials Technologies, who's part of my microwave team. I'm also showing a heat protection. This is also for dust to prevent the simulant from going up into that applicator. In a real case on the moon, we will need some type of protection against dust and also to prevent radiation heat loss, but it doesn't have to be thick. This thickness had to do with me wanting to be super careful and make sure we're not in as hard a vacuum as we would be. So this is part of my experimental design. And the simulant container holds, a lot of simulant. And normally, so this little box inside has nothing to do with the microwave heating process. What it does is help protect in the early stage when I'm pretty cautious that I don't want to have any situation where the stainless steel can heat up and be compromised in some way, because you could picture a situation with overheating, melting, and actually burning through that stainless steel. So we wouldn't want anything like that to happen. This hot zone is defined by a radiant heat source. Whatever you make that radiant heat source as a kickstart will give you the ability then to directly couple with the Highland simulant. And I'm going to talk more about that. That's really important to understand. This is an engineering design. There's a lot of science behind it, but it's about doing it, see what works at the same time, and being cautious along the way, because microwave can go very bad very fast if you're not careful. So I'm focusing now on top-down ISRU microwave paving. In order to do the modeling, you need dielectric and thermal properties, and that'll be very important. That's what controls your microwave heating. The system design will also have a strong effect. So you have to understand that one system that no matter what you do fails, make some changes to that system and then it can work. This has a lot of engineering in it. The goal is to minimize that energy input. So there's going to be a lot of ways to accomplish this paving and construction in general, but the energy will be at a premium. So I look at that figure of merit in kilowatt hours per kilogram. And so really, I want to minimize that FOM. So NASA, I've had many debates with them. They'd like to flip that into the kilograms per kilowatt hour, because then you get to maximize your figure of merit, which is normally the way you look at things. But from an engineering standpoint, I would like to be able to say how much mass I need to solidify, and then, figure that out by the thickness of that paving and then the dimensions in the XY directions. And then from there, calculate how much energy input I need to do that. So that's the way I look at things. On the right, I'm showing some dielectric measurements that were done by Ron Hutchin at Microwave Properties North. He really is a master of this. It's a very delicate kind of measurement. You're actually, it's called cavity perturbation method. You're actually heating in a conventional way and then dropping it into a low field microwave. And so these were too high temperature. And the things I want to point out here, on the left, I'm showing penetration depth, and the right, tan delta. So the blue line is tan delta. Tan delta is a measure of the heating through dielectric loss. And penetration depth is how deep those microwaves are penetrating. So you can see that as you couple more or suscept better, so you have better conditions for heating, that it's intuitive that you don't have as much energy to go into higher depths. And that's really a good thing, because if you're putting microwaves 1 meter deep, you actually don't have enough energy in that whole volume to heat it very much. You're not at a temperature that's significant. And what I look for is a region where the penetration depth collapses, and the tan delta is at a level with, through much experience and a little bit of modeling, that shows that you're now in the zone for, in this case, softening the glass and vitrification. And yet this depth is still really good. So at 100 millimeters, that's the target that NASA gave me at 4 inches. Okay, so, but we have to get it into this zone. And without it being, somewhere, 6, 7, 800, without getting into that zone, we're just wasting energy from the microwave. So a radiant heat source is super important to give the kickstart heating, but you don't have to heat that whole volume. You just need surface heating, because then that will re-radiate inward and you'll be driving that microwave energy inward. So just with anything, the practical view of it, when you're firing ceramics and you're heating them from the outside in, just a conventional way. It's radiant heat. It has to move in. You have to heat extremely slowly, because the ceramics usually have a very high heat capacity. It takes a lot of energy to raise its temperature, and it usually have very low thermal conductivity. So you just have to gently baby it along. With the microwave, you're able to you drive it from that depth. So once you have that surface heated, even just less than a millimeter, you're driving it inwards more efficiently. And I have a lot of data showing this with many different materials. So, some people can argue, well, it's why would it be more efficient, or it's not more efficient? I have so much data that I'll drown you in it sometime if you ever want to have a conversation. Okay, so again, starting out, I'm not sure what's going to happen. Top down heating. This was actually in my lab. So this is in a cover gas of argon. This was my major concern, is that we would have something called mud flat cracking. And if you've ever seen like mud that has dried out, it's got this pattern, these cracks. What that is the drying of that mud. It's coming out from the surface and it can't shrink laterally. So you have a condition where it just sets up cracks. And this is what I was really worried about. And there it is, of course. But what happened is, well, then I moved into the vacuum and got some outgassing and things got a little worse. But at the same time, what happened was I was able to control the microwave power time input such that I'm not getting actual shrinkage. I'm vitrifying. I'm basically, softening, melting that glass so it's gluing together, but I'm not forcing much shrinkage. And so that's a good thing. So we're getting some solid pieces, and then we're making progress as we understand better how to input that microwave. And again, this is an engineering project. There's a lot of science in it, but until you do it, science sometimes backfires. And so, well over a half a kilo, and still even larger depth, better figure of merit. And finally, this piece, this was a small designed experiment. Finally, we got to a stage where we've got 1.4 kilos, which is pretty good size. It's got good thickness. It's got, good figure of merit. So I'm starting to develop a process that's working. Now I'm just recently cutting these apart and doing measurements, so I don't have that data yet, but this is looking good, like a solid paver. And again, the size and shape are defined by the kickstart heat, okay? On the right, I'm showing the first demonstration of microwave joining. On the bottom here, this was the bottom tile that we put that was already microwave sintered. I sacrificed, one of my not as good tiles and put some, powder on the top. So the CSM went on the top, and it was then heated, and you can see that it's solid, it's joined, it doesn't come apart there. Now I tried this completely ISRU and it didn't hold together, but this tile was cold, and I actually didn't think that it would I had, 2 attempts at this. I didn't think that it would, but I thought that at some stage I could drive that heat deep enough, once I get enough control to be able to reheat this tile. But in this case, what I did is I added a little bit of something that has a lower melting temperature that suscepts better in the microwave, a very little bit of something called frit. And so that went in, and so that's not 100% IRU in this joining. So if this were hot and I pushed powder on top of it, I'm fairly certain I wouldn't have a problem continuing that joining. But another concept is to be able to just keep on driving that heat deeper. And instead of taking separate tiles and joining them to build vertically, that we could also drive down into the regolith bed. Next steps are really to go into a larger vacuum chamber. This is at Marshall. They call it the V20, very large, high vac, dirty system. And actually, this is Olivia Gilbert. She was my co-op engineer, and we went down there to have a look at the V20. And right now, Icon has just recently tested their robotic arm in the V20 in a high vac. I think it's 10 to the minus 6 torr capability. I'm not sure if they were at all the way to 10 to the minus 6 or 10 to the minus 5. And they tested it in cryo temp and also warm. So as warm as would be expected on the surface of the moon, something not needed more than 70 C. So that passed all those tests. Super important example. There was no simulant in there. So this was just the robotic arm testing. But there will fill a very large powder bed in there in order to do sintering experiments. Now, my work, we're collaborating also with Icon so that we would use their robotic arm to move our microwave system. So what we have is a microwave waveguide. So we're coming through the V20 port, and the magnetron to supply the microwaves will be out here. And then we're putting down the waveguide to bring the microwaves in. And in this case, we're showing a horn type shape, but really this will be replaced by that multi-mode system that I showed you. An applicator applies the microwaves, and this would be like representing the surface bed and the area that we would be targeting. This system is not designed to be controlled automatically. We would use that robot arm and have a link up with it to move this around to be able to accomplish the scanning that you need to do the paving. And that was designed by John Gerling. He's a part of my microwave sintering team. So back from the past again at CereLink, we developed this system, concept design to go. This was doing Martian work, and that we would have the microwave system boarded on a rover, and then underneath you can see a radiant preheater. So that was the idea, that we would use that, and then microwaves in here, and that system would then be mobile. So in this case, for the first demonstrations on the moon, this will be stationary on like a Eclipse lander. And then this is like a nice little schematic done by my students to try to give an understanding of this would be our multimode applicator that somewhere Icon's arm will be able to attach to it and move it around. It might be more realistically to that waveguide. And as part of this system, there would be, in this case, a scepter, but I'd really like to move towards using a radiant heat source like solar, because that's very doable. And I think it'll be a little bit more energy efficient, but also it'll be practical. But this totally will work. So our first design is going forward with this kind of a thing. And as I said, anything we do on that susceptor is going to give us kickstart. If this was round, if this was shaped like anything, that's what the hot zone would be. So it's very interesting. This is some Faraday caging to prevent microwave leakage. And then this would move on the powder bed. And I'm showing 7 millimeters per minute is a calculation from the work that I did at Marshall. And it's really kind of a back of the envelope for what we think we can do now. I actually think we're going to be able to move faster than that in sinter once we get this process really worked out thoroughly. I'm switching modes now, and let me check the time and make sure I'm okay here. All right. So, I've said before how important a good fidelity simulant is, especially in microwaves. We care a lot about things that will cause higher suscepting, and iron is definitely one of them. So the iron in the Highlands region, some measurements that are shown in the lunar source book, an average of around 1, as low as 0.1, as high as 1.8, but that range could be even higher than that. So what we did with our synthetic lunar simulant, which I call DHS, is we added iron to the glass component. And we used it through a carbonyl iron. And we know that in the end, we did have iron because we did X-ray diffraction, and we clearly showed that we kept those peaks. So we were very careful not to let oxygen attack it at any stage in that processing. My master's thesis student, Cooper Howard, actually developed these different components of the DHS simulant. And he also worked on getting calcium into the diopside and the enstatite, so the pyroxenes, as substitution, which it can go in there. And it, so that was a process that he's developed. He was more successful on one of them than the other, but we decided for this project that we should stick with something that was easy to control, and we knew what we had. So we went with the addition to the glass. And I also want to point out that 1% iron, 1 weight percent in the glass, is the closest match to the baseline material because we're taking glass out as we're adding iron. Okay. So just pointing that out. Also, this actually should be SiO4 for olivine. So olivine, I'm showing this as Mg to SiO4. Olivine is actually got iron on that site, on the magnesium site, but this end is really called forsterite. So it's variable how much iron you can have on that site. Just to make things very simple as a baseline, we decided not to use any iron anywhere except in that glass. And then on the left, this is showing the system, the package that we set up. I call them thermal packages. And this is a high temperature refractory. I know the dielectric properties of it. It handles very high temperatures, for safety, but also for microwave transparency, because we're shooting microwaves right through this. And then we have some silicon carbide susceptors, which are actually a composite that I developed. I call them thermsep. So it's got a proprietary composition, and they're just really great for microwave processing. And then the sample is sitting here. And we have a 2-color optical pyrometer that we can sight on that sample directly, and we can also sight on the susceptor. So that's our setup. I want to point out that your setup, it's going to influence everything about this process. So every time you change that setup, you've introduced a variable that is completely unknown. So for example, if you have a larger volume inside, you have radiation heat loss, certainly, And if you're running in argon, like these experiments where you have heat loss through other mechanisms too. So you really have to be very consistent and define your thermal package extremely well. The mass and volume of your susceptors will have an effect, the mass and volume of your sample. So this isn't an ideal situation. It's what we had that we could do quite quickly. I would much prefer a bigger sample. I'd like my sample to be larger, higher mass than my susceptors in this case. But this is where we were. I just want to make sure everybody understands that. That is going to have a huge effect on your results. Okay, so this is what we came out with. And I want to first focus on the right on this graph that you can see the aim was to hit 1200 C and then turn the microwave off. They're all running at the same power level with the same thermal package. The 0 iron is here, and you can see absolutely it is taking longer to get to that 1200 C. So it's not heating as vigorously as when we had iron. This is the 1% iron, and this is the 10% iron in the glass. And you can see that 10% is really heating very vigorously. And in less than 30 minutes, we're hitting 1200 C. This line here is the optical pyrometer on the susceptor. And you can see that it's vigorous heating at first, but it's not heating as high as that iron simulant, high iron simulant. And this is also intentional, that we design these thermostats so that we don't want them to continue to heat. We want them to turn over and not compete for microwave energy. So that's why I say it's even better if you have a source that you can just turn off, that it's not related to the microwave at all. And then you see at 1% still very vigorous heating, and we're getting to less than 40 minutes to hit that 1200 C. So then when my student, this was a BS thesis student, his name is Jay Stearns, and he actually is a full-time employee at Corning Glass, and they sent him over to do his BS with us at Alfred University. And he was really puzzled when he saw what these samples look like. With 0% iron at 1200 C, we have a really solid, strong sample. And all of these iron-based materials were still friable, with the 1% iron actually being harder than the higher iron content. So what's happening here is because these runs are so quick, with the 1% not quite as quick, right, as the 10%, there's something called heat work. The whole question about temperature is very confusing when it comes to microwave. We are always assuming some sort of uniformity of temperature, and that you're really measuring either the surface with a pyrometer or something nearby the surface with a thermocouple. And what's happening in the microwave situation is that you're directly heating internally. And so your surface temperature that we're measuring here is quite correct. And it might even be true that it's just as hot on the inside. But because it didn't have enough time, the way glass behaves, it needs a certain amount of heat and time. So it's called heat work. So hitting a certain temperature with a glass is not going to do it. We need time for it to move around in order to give it some viscous flow in order to hold this together. Okay, so now I just want to talk a little bit more about microwave materials interactions. Dielectric properties of materials. We need to know these things in ceramics and glass. In metals, not so much, because you have electric conductors. And so engineers that aren't really familiar with ceramics don't often run into this, or don't, depending on what field they're in. But I want to just point out that polarization is the basis for the dielectric response. And you have different mechanisms for polarization. And those mechanisms are both frequency and temperature dependent. So something like electronic polarization happens at such high frequency, we never have to worry about losing that if we go to high frequencies. But in this frequency range, we have quite a bit of orientation polarization and space charge polarization. So you can see that here. And this polarization drops off, space charge goes out first, orientation polarization drops off as you go to higher frequencies. This is because those mechanisms of polarization, they can't follow the field. So it's like the field is flipping back and forth, and certain polarization mechanisms can always keep up, like electronic, and others start to be frozen. They just, once the field switches the other way, they can't move at all. It's like they're frozen. And there is an analogy with temperature and frequency. So higher temperatures, you put more energy in, you warm things up, you're better able to flip polarization to align with the field, right? But then as you go to colder temperatures, you might freeze in those polarizations, and then they don't add they don't add to what we call the dielectric loss. And the dielectric loss, and I'm actually going to show that on the next slide. So this is the complex permittivity, which some people call permittivity dielectric constant. It's very common to call it that, but it's not constant. And so I prefer to call it permittivity. There's a real and imaginary part. The real part is where it can follow the field, align in the field, and add to the polarization. The imaginary part is the dielectric loss, that it's lagging. So it's not completely, it's not frozen in, it's trying to follow the field, but it can't quite make it. And that lag gives heat. It's like an internal friction, and it builds heat. So just kind of electrical conductivity, which people really usually understand better than they do dielectric properties. When you have high electrical conductivity, you're reflecting a microwave field. When you have a highly resistive material, it can be so highly resistive that nothing is really 100% transparent to microwaves, but it can be fairly transparent, and microwaves go right through it. Then somewhere in the continuum, you get to a place where something can absorb microwaves very vigorously. And I've put down tan delta about 0.1 here. Really, it's less than that. It's probably about 0.02, and it kind of depends on the material. And this is thinking with 2.45 gigahertz, but this is really a rule of thumb, kind of trying to give the understanding that there's a range, and there's a place where materials, dielectric materials, can really absorb well. So maybe at room temperature or cryo, they might not absorb well, but you bring them up to a couple hundred degrees, and all of a sudden they get into that sweet zone where they're able to suscept, their microwave penetration depth collapses, and there's a concentration of energy, and it heats. Also want to point out that power density is proportional to frequency. So you go to higher frequency and you're really generating, better power density. But on the other hand, your penetration depth is inversely proportional. So you want to be able to get some sort of depth so that you can really get a lot of volume heated. And 2.45 gigahertz is kind of a compromise frequency. Everything is a compromise in engineering. And this table is 2.45 gigahertz just at room temperature, but I think it's really important to kind of orient you in where the Highlands regolith is. These are actual measurements of regolith taken by Marty Barmetz, and I'm sure you didn't have too many samples, but showing that it's a pretty low tan delta, and it's fitting somewhere in there with porcelain. Whereas the Mare material, much higher dielectric loss, much higher tan delta, so smaller penetration depth. It's going to be a better heater at lower temperatures than the Highlands. This material, it really acts like a basalt. So I can look at the dielectric properties as a function of temperature. This is just a snapshot at room temperature, and get a real sense of other materials that I've worked with and understand how this is going to behave, at least dielectrically, not necessarily physically and how it sinters, but have a real understanding. And this is where JSC 1A, and this was actually 1AC, fits in. It's reasonable. It's a reasonable proximity to the mare sample that Marty Barmatz measured. Okay, so one thing I want to point out, I talked about temperature being really a tricky thing to try to understand, and there's been a debate in the microwave community for many years on whether microwaves are actually causing an accelerated diffusion, or if it's just that it's hotter there and you're not measuring the right temperature. And from the engineering point of view, well, you know, what works? So there is a scientific explanation for enhanced diffusion, and the best one I've seen is on the ponderomotive effect. That's really getting into the weeds. But this data is something that convinced me that microwaves absolutely are enhancing heating and diffusion, and that it is really the clearest evidence of accelerated diffusion. So there's 3 samples. This was work that was done at CTech Innovation in the UK. My company CereLink licensed their patent into North America and developed microwave assist technology here, which was a combination of microwaves with some kind of radiant heat. It was electric or gas. So at that stage, this is not really looking at susceptors, because it was separate control was the concept. And these 3 samples, you can see just a conventional regular heating, and this is linear shrinkage, which is a dilatometer that you use to see that. You press a long skinny pellet basically, and then see how that shrinks. And in a conventional way, this is alumina, this is, you know, a high quality sample that is just one material, so it's not a composite like all these other regoliths are. And you can see how it shrinks and what temperature. When we switch the microwave on, so this is actually CTech doing this, switch the microwave on, you can see that at a lower temperature, this is measured on the equipment, the dilatometer, a lower temperature, we're getting shrinkage. So that shrinkage is caused by enhanced diffusion. So this is some really good evidence. And then a third sample, so this really, it shrank at a lower temperature reading. And when the microwave was switched off, so at first it's combined, switched off, you can see it regains the slower, higher temperature need in order to cause the shrinkage. So that I felt was very strong evidence, very useful. And I just wanted to share that in case anybody says, oh, well, microwaves don't really do anything. Yeah, they do. Okay, to summarize, NASA will build the infrastructure on the moon. Well, it's NASA with also industry, and other countries too will be involved in their own efforts. Artemis 3 will be a landing pad demonstration. ICON is developing the flight hardware and the robotics. They also have a laser DED system, which will be interchangeable with our microwave system. My company, Blue Star Advanced Manufacturing, has a team, and we're focused on the microwave sintering, and that's ongoing right now in a second contract I have with NASA. And this is a focus on ISRU and energy efficient processing. All the wonderful people that I've worked with here are acknowledged. And any questions?
Yes,
Oh, you have a question?
well,
Do you
I
want to go
mean,
first? There's none online. Yeah,
I don't wanna hijack, but,
Alex is just saying thank you.
can you hear me?
Yes,
Alex?
yes.
Yeah, very nice presentation, thank you so much.
Oh, thank you.
So. Let's see, where do I start? Like, how do you design your waveguides? Do you have like, is there like a software that makes this easy for you? Or do you have to like apply your RF knowledge every time? Because it seems you can have waveguides that, you know, are long, are complex and have elbows and everything. Which obviously, yeah, the waves are gonna go, you know, but how are you gonna have them heat uniformly when they come out of this?
Well, so actually, the waveguide, there are standard, they call it ISM, it's industry, scientific, and medical frequencies, which will have different, basically waveguide sizes that go along with them. So 2.45 waveguide has a couple of options that are commercial. So we use as much as we can COTS off the shelf. But
I see.
basically,
Okay.
the waveguide, what we want to do is minimize our losses. So part of that waveguide design is for that. And in terms of uniformity, what we're doing is we're not really sintering in a waveguide. We're taking the microwaves and feeding that thing that I showed. I'm calling it a microwave applicator because it applies the microwaves. Wait, it's right here. So this actually is quite large. This is a waveguide. So this is like a microwave chamber, which we call an applicator. And what this does is allow bouncing around and mixing of the modes. So it's like stirring the modes to give a more uniform electric field. So instead of looking for the highest field within a waveguide, we're just mixing it and deciding we're just going to impinge a uniform field onto the surface. And then the definition of our hot zone has to do with where we kickstart the heat. So I think that what people have a problem with is that they want to microwave sinter without using any radiant heat that helps put them into the zone at which the material is actually suscepting.
Mhm.
And that you can do it in a waveguide, you can do it in a single mode, you can do it, but it's small scale and it's actually less reliable. You can also do it with a very high frequency, variable frequency, very expensive equipment, which is fine for something like this, but it actually is not very robust. You can go to very high frequencies and then drop down to lower frequencies. You can pulse on and off the microwave. So these are different strategies people have tried. And I've of course tried all of them, right? As being an experimentalist. I love high frequency, millimeter wave, gigahertz, love it. But the trouble is that equipment isn't gonna fly. It's not gonna sit on the moon. High power gigahertz it can't handle thermal swings. But so this is, it's the trade-off, and 915 megahertz or 2.45 gigahertz. As long as you take those modes and mix them, you have a uniform field. But then you need the other part, and that is to get to the sweet zone.
So I see, because I guess what you call an applicator is just the last part of a guide, right? You're still sort of guiding it, so but this time you're mixing it so that it's uniformly going into the simulant container. And so what you show at the bottom is the simulant container, and you just have a mold, so to say, they are in the middle.
It's a piece of zircon refractory. This is a high aluminum refractory. It's flat, yeah, and it's in the middle. And so because of that, microwaves can leak out the sides here. So that's why you'd need an RF shield to come out around it to protect from sideways leakage, which is easily doable. That's not a problem. But so what it is the microwaves are going all through here. And so that's all the way to the edge here. So what I did is I put something, oops, sorry. I put something underneath this in this shape so that I could kickstart it there.
Mhm. And around the shape, is that also regolith?
Yes, it's all the same regolith. It just, it didn't heat. And it
Okay,
wouldn't heat, it wouldn't heat. If I took this little box away, it would look exactly the same. I don't need this box. This is
Yeah.
doing nothing. It's microwave transparent. It does absolutely nothing, except it would thermally contain things if it went very bad, if it went
Yeah.
wrong.
Yeah,
Yeah.
which we have done.
Yeah.
You
Oh,
know what
yeah.
I mean, okay.
Yes, we've melted things.
Melting, burning, yeah.
Yeah.
Okay, interesting. So I see. So your microwave heating happens in this node in the middle anyways.
No, the microwave, this is designed, and this was modeled by Hal Kemery. This is designed so that the microwave field all through here, so the microwave field underneath here would all be the same. It's all the same, but once this starts heating, it preferentially grabs that microwave. So
But why would it start heating always in the same spot?
I can move that spot anywhere I want in this box.
Okay.
Under this applicator, if I wanted to make a little spot right here that I centered, I could do that.
Okay, thank you. I'm gonna start hijacking.
I will, we can talk offline. I'm happy to talk
Yeah,
some more about
And
this.
we
Yeah,
will, and we will, yeah.
yeah.
Okay.
I think Joseph had a question and then Nico had a question after.
Thank you for a wonderful talk. I had a thought and a couple quick questions. My thought was, first of all, thank you for making your figure of merit be linear in the energy. If you want to see a screwed up figure of merit, look at the price to earnings ratio in finance, which goes to infinity and minus infinity as earnings go through zero. I'm curious about two things. One was, have you ever tried, and maybe you said it and I missed it, but adjusting the frequency so that you're heating at particular depths and then either strobing through some frequencies to cover a certain range of depths, or just trying to heat something below, let's say below the top layer. And my other question had to do with the bubbles. And I'm wondering if the length of time, you mentioned later in the talk that if you heat it for a long time, you got a stronger result. And I'm wondering if that's just a matter of letting the bubbles come out, and how would how is that affected in 1/6 gravity, where the bubbles aren't going to come out nearly as fast?
Okay, so the second question first. It's not because of the bubble thing in the it really is, it's called heat work or work heat. And it's really about viscous flow of that glass. So it just didn't have enough time. It was, it's called maturing of a glass.
So if you heated it to a higher temperature, you wouldn't need as much time because it would flow more quickly?
Yes.
Okay.
And that's exactly what you do.
But bubbles also have to do with the viscosity.
So bubbles do, but so that so we didn't have, so bubbles weren't, there's bubbles in there, yeah. But the big thing, see this one, it's got bubbles, but the big thing is that this stuff is solid, even with the bubbles, and this stuff is not. And that's a time effect. So
Yeah.
there just wasn't enough time for that glass to mature, we call it. And glazes are like that too. You can go to a higher temperature and get there, or you can just leave it for longer time.
And do you think gravity doesn't have a big role to play there? My intuition says that maybe the gravity isn't as much of a big deal there. It's just sort of very local mixing.
It's so I don't have too much experience with lower gravity, but the gravity is not really the issue. that's a bigger thing that this is done in a argon cover gas than vacuum. So, but you know, so these bubbles, yeah, if we left it a longer time, maybe these bubbles would work their way out. Maybe that would be really affected by the difference in gravity. Yeah, that could be. We don't want to produce bubbles. We just want to soften that glass and glue everything together. And that, it's called maturing a glass. And that's going to take time wherever you are, but certainly we have to do some low gravity experiments and see what happens there. If there's a problem getting the glass to move, it'll probably wet and wick, but we need lots of work to understand it better.
I would think in a vacuum, you might actually do better with the bubbles because they would want to expand and that would tend to get them to breach the surface and get out of there.
And in a vacuum, you have another effect, and that is that it changes the volatilization temperature of things. So a temperature that works in a cover gas might be much too high in a vacuum. And that's, I think we're learning that.
How about tuning the frequency to heat at a particular depth?
Okay, so you have variable microwave frequency units that you can use, and yes, that's doable. It's doable. It's finicky. In theory, that makes sense. I'm not sure they're going to be able to really have a system robust enough to do that. So we're looking at solid state instead of a magnetron and being able to, you know, so it's an engineering problem. It's not a science problem on the moon. In the lab, it's different. In the lab, yes, if you go to higher frequencies, what you can do is you don't need any radiant heat. You need no susceptors or anything. At 28 gigahertz, you will really, your penetration depth is collapsed. You're really going to, right there in the, you know, top surface, you're going to heat vigorously, and that will re-radiate inwards. You'll be able to, and then if you wanted to then drop the frequency, you can do that. But the variable frequency isn't going to go as high enough, because that's a gyrotron. That's a whole different system. So certainly, like, it's definitely possible. It's definitely a thing that can be looked into.
I was wondering if you heated from the bottom up, could you make the bubbles come out more easily because the upper material is still more easily penetrable to the bubble?
Yeah. So the if you see this here, and also I noticed Alex ran into this too. This is the bottom of this sample. It's hotter on the bottom. The reason that it's hotter on the bottom is that it's sitting on something which is trapping the heat. So it is radiating in all directions. It's just in the bottom, it's, you know, re-radiating back into itself.
Yeah.
So to really properly do this, you'd have to have it floating. And so it is hotter on the bottom. But in terms of the bubbles escaping, in glass and in ceramics, like more traditional ceramics, you use a fining agent in glass to get the bubbles out. You put something in there that helps escort them out. And so we're not going to be able to do that here. I'm not actually really concerned with the bubbles, especially spherical bubbles. Those actually give some toughness to your material. And we're not going to have our biggest problem is not going to be the strength of this material. So, you know, it's already better than concrete.
Thank you.
Okay.
And then we had a question in the chat from Nico. If you're not able to see the chat, I can read it to you too.
Yeah, I don't see the chat. Yeah.
Okay. Nico asked, have you tried using a binder-like material that can be extracted from the regolith? I personally use aluminum powder with LHS1 for solar sintering. And he
So,
also uses that to lower the melt temperature as well, I believe.
so, well, you know, you can let's just throw some mare in there and you're good. So what we're trying to do is, it's the first step. It's before we can do any processing on the moon. It's a landing pad. It's the first step. And so what you're suggesting is very interesting, and you know, I think it's a good idea. But I haven't really worked on that yet. I mean, be happy to talk about it offline. To have something mixed in with the regolith that has higher ability to suscept at lower temperatures is absolutely something that you can do. But you don't even need that. If you just sprinkle a little ilmenite on the top, it works. I already tried that. But we don't have access to ilmenite in the highlands. So mixing it in, yeah, that's doable, absolutely doable. But the less processing on the front end, the better for just to get started with.
I see said thank you. And then I'll ask one quick question that follows up to that, and then we can end it and I can ask you some questions later, since it's already
Okay.
12:10.
Okay.
But my question was related to that, so actually, we'll let someone else ask the question.
Okay.
Yeah, because I can ask you more later.
Okay.
Hello,
you-
can you hear me?
Yes.
Okay, thank you so much for that amazing presentation. I'm overwhelmed. I have so many things that I would love to talk about because I'm researching on a similar, absolutely similar topic here in Luxembourg. I would like to ask you, you showed the design of the horn that would be that would be actually working, yeah, on the surface of the moon, exactly here. No, the previous one.
Oh, okay. Sorry.
Yeah,
Oh,
yeah,
okay. Yeah.
yeah. So it's great. I want to understand when you explained your microwave applicator, where you have laid down the regolith simulant bed and then you are just heating that square area. The applicator has to be closed. To create a multi-mode applicator, you need to have closed compartment. This horn, is it going to be acting like an applicator covering some depth of the, like, how is it going to act on a bed of regolith open in the air?
So you're right that an applicator, multi-mode applicator needs to be closed. But the design of that applicator, so this horn is not really what we're going to use. We
Okay.
did a lot of work with all different shape and figures. So what we're really using is this. This
Right.
is
Yeah.
and so this is designed so that it can bounce microwaves around,
Exactly.
and it's been modeled and it's got a uniform electric field that will impinge. Nothing's perfect. It's not 100%.
Agree.
But so that's what this design is. So the waveguide feeds in it. With a horn, we weren't able to get, you know, we weren't getting mixing.
Yeah. Yeah.
Yeah, so
Okay.
I mean, you can do different things. You could put baffles in here. You know,
Yeah.
this is like a kitchen microwave feeding
Exactly.
down.
Exactly. Yeah. Yeah. We just
Yeah,
don't have a turntable, but we may have a stutter to move the wave around
right,
and create
right.
multi-modes. Yeah. So I
Right.
mean, then we cannot use this kind of design to roll over a regolith bed and sinter a landing pad, right? Because this means we have to take a sample, put it in the applicator, and then take it out and use it as a brick or a building block.
Okay, so no, it's not really the sample's not in here. This is
Is at the bottom.
yeah.
Yeah. Yeah.
And so that's
Okay.
simulating a
Okay.
powder
Okay.
bed, and we would move this applicator over that
Ah,
surface.
okay.
What
Okay.
we
Okay.
have to do is protect it So, so we're not going to have an electrical close by having metal on the bottom, but we will have a barrier that will allow the microwaves to come through and not let dust come up. And
Okay.
we also have to have a way to prevent radiation heat loss from that surface. We need to-
Exactly. Yeah.
Yeah.
Yeah. Especially on moon, like there would be ultra
Especially-
high vacuum. So
Right.
yeah, cool. Great. Thank you so much. Thank you so much.
And anybody, you're welcome to contact me and we can talk offline. It's fine.
Okay, cool. Yeah, I think since it's 12:15, thank you for presenting to FSI. And I think we'll end the recording. And then I'll probably email you some questions too.
Okay.
All right, well, thank you so much.